This is lesson 7.4, the the heights of NBA power forwards. Here is the check for understanding. For this is the power forwards lesson. Tomorrow is the shooting guard lesson. So this tells us that the heights of young women follow an approximately normal distribution with a mu, or an average, of 64.5 inches and a standard deviation, sigma, of 2.5 inches. Let's calculate the mean and the standard deviation of a sampling distribution of X bar for simple random samples that are each size 15. So the average of all these X bars, the average of all these samples will be the same as the average that we're given of 64.5. So again, if I took a whole bunch of these, simple random samples, on average, they would reflect the population that they are sampled from. So that's that. The sigma here, this is the standard deviation for, I like to think about this is just for one single woman, or a sample size of one, okay? Meaning, on average, young women are this tall, and on average, if you picked one woman, uh, her height would be 2.5 inches, would vary 2.5 inches from the mean on average. So if we increase our sample from 1 to 15, what's happening is oops, that's not where the arrow goes. What's happening is our sigma is getting smaller because we're increasing our sample size. So we're dividing by the square root of n, okay? So we take the 2.5 and we divide by the square root of 15. 2.5 divided by root 15. 0.645. All right. Next, interpret the standard deviation. So this is good. You always got to be able to do this, folks. So remember now, what are these? These are numbers that describe SRSs of size 15. So on average, if we took a whole bunch of samples of size 15, the average would be 64.5. And in a whole bunch of simple random samples of size 15, the mean height of the women would vary from the true mean by this much. On average, these samples will vary from the mean by 0.645. So it was 2.5 inches when we were only sampling one single woman. When the sample size increases, remember, a rule of thumb is that standard deviation goes down. So that's what happened. Number 3, find the probability that the mean height of a random sample of 15 young women exceeds 66.5 inches. So I have a curve labeled, my mean is in the middle, and this is actually adding one standard deviation from here, from here to here is plus 0.645, and then from here to here is plus 0.645, in case you're wondering where those numbers came from. And likewise, going the other way is minus 0.645. You don't need to go to that length, but I thought it was kind of interesting because we want to know the probability that a sample exceeds 66.5. So I mean, right away, here's 66.5 way over here. We've got, here's right up the middle. That's a standard deviation of 0. Here's 1. Here's 2. This is 3. So I already know my z-score is going to be bigger than 3 by looking at that. And if I zoomed in, I want to do this shade to the right. So it's not going to be very likely, okay? So the probability that I would get an X bar, an average of a sample that is greater than 66.5 is what? To do that, I need to find the z-score. The formula here in the quick notes for a z-score is right here. Okay, so let me see if I can keep them both in the picture. The X bar of the sample was 66.5 minus the mu, the population average, which is 64.5, divided by my standard deviation. From my samples of size 15 have this for the standard deviation, not this, okay? And when you do that, it's going to be a little bit bigger than 3, I think. I hope, if my picture is right. Oops, 66.5 minus 64.5. So we're 2 above the mean, which actually we needed a calculator for that. Then divide that by 0.645, and sure enough, we are 3.1 standard deviations above the mean. You can look this up in your green packet. If you do that, just a reminder, if you look it up in the packet, let me shade all of this in orange. It's going to give you that. And it's pretty much like 0.99, I think. But if you get that, remember this little sliver over here is that I want. This little sliver will be 1 minus 0.99. Let's do it on the calculator too. I'm going to do the normal CDF button. My lower boundary is 3.1 right here. And my upper boundary, this is going to keep going forever that way. So if I wanted to extend it just to prove my point, 99 is what we put. So this here is 3.1 for my z-score. That's my lower, and my upper is 99. So wow, that's even smaller than what I was getting from my green packet. So what that is scientific notation. We could jot that down. We can take it all the way. So this would be 9.67 times 10 to the negative 4, which if we do move our decimal four places over to the left, we got 0.1230, So maybe I was a little bit, I'm close, but maybe that's not quite enough. Maybe it's got a couple more nines, like 0.99 or something like that, which would make this one 1 minus 0.999. A little closer anyway. Yeah, that's pretty much what that is. So here I summarize it in blue. There's about a 0.001 chance, you can see that in the calculator, and that's pretty much what this is. That 9 would round up to 0. There's a 0.001 probability that a mean height of an SRS, a simple sample of 15 young women, exceeds 66.5 inches. In other words, that's pretty much never going to happen, which leads to the last question. Suppose that this does happen, okay, at a local college, okay? Based on our answer right here, does the data provide convincing evidence that the mean height for all the women at this college is greater than 64.5 inches? And the answer is an emphatic yes. And blue is what the book says, and then purple is I wrote it another way. So because it's very unlikely to get a sample of 66.5 or greater by chance alone, that's just not likely to happen even in a random sample by chance, there's convincing evidence that the mean height for all the women at this college is greater than 64.5. That's what the book says. I phrased it this way. If that, like, our entire graph here is operating under the assumption that this is indeed the average, So if indeed 64.5 is the average, then the odds or the probability, odds is probably not the right way, the probability, we'll say prob, is that all right? Probability of obtaining a simple random sample with an average of 66.5 is 0.001. This leads me to believe the assumption of the average being 64.5 is wrong, in favor of the average being above or greater than 64.5 inches. So there you go. Thanks for watching.